Hello everyone. In this webinar we are going to talk about accelerometer calibration and its different variations. Before we start, let me show you our setup and explain some theoretical basics. We are hoping to make it interesting and worthwhile. Our first step is to talk about some theoretical basics. In vibration testing, it is essential that all our accelerometers which we are using during our tests are accurate and reliable. An efficient accelerometer calibration RULA software makes this process of calibration really easy, fast, and the procedure of accelerometer calibration is really well developed. Now let's talk about accelerometer types. There are two of them. On the left side, you can see a regular piezoelectric accelerometer. It is a time-proven device with a wide frequency range, and it can measure big acceleration values. And the second type is called microelectromechanical accelerometer, or we call it MEMS. It has a narrow frequency range from rather low frequencies up to 3 or 4 kilohertz, and it is usually used when we need to measure really low frequencies like 0.1 hertz or about so. We can apply our accelerometer calibration in different spheres like serial sensor production, laboratory tests, research, and development. Also, it's very important to check your sensor specifications before you use it in your tests. In that case, you'll need to calibrate your accelerometer and check if your sensor is still healthy. In our software, we met all the requirements during to ISO 16063 standard. Here you can see all its parts which we met in our software. And at the last part of our webinar, we will talk about resonance testing in accelerometers, and it was made by the last, you can see it here, standard. And now let's continue with our calibration sets. Your regular accelerometer calibration set must have a vibration controller, an amplifier, some dedicated software, shaker. Sometimes you may need multiple shakers in case you need to cover all the frequency range. For example, you'll need one shaker for low frequencies, another shaker for middle range, and some kind of a shaker for higher frequencies. Also, you'll need a reference sensor. In the next picture, you can see our regular setup. Here we have our RLC21 controller, RLA 200 amplifier, a laptop with our software. We will use this probe cell. On the left side, you can see a middle range shaker, and on the right side, here you can see an APS spectra shaker for low range frequencies. Now I'll turn on the camera. I think you can see it. Here we have our RLC25 controller, RLA 200 amplifier. We are using Tira TV51110 shaker, and on the back you can see a spectra shaker for high frequencies, and here you can see that there is a setup for resonance search. Our first method of accelerometer calibration is called back-to-back. Here we will use RLC controller. It can be RLC21, RLC25, or RLC21M. You need an amplifier, shaker, and two sensors. The first one is a reference sensor, and the second one is sensor under check. Here you can see that you need to place both accelerometers really close to each other and place them on the shaker. On the bottom there is a reference sensor, and on the top of this sensor we place a sensor under check. In this method we go through all our frequencies in the range. We measure sensors under check voltage and divide it by a reference sensor acceleration. In that case, we get the sensitivity value. After that, we measure all the frequencies and calculate the deviation. Here on the right side, you can see our formulas. After this webinar, you will receive papers with an explanation if you need. And now we are ready to go to this probe cell. Here, let's press Create Test in our sensor calibration. And our first step is to select our sensor under check. Let's go to our sensors database. Here you can add your sensor and change its parameters. Here we have our sensor. It's BNK 4613100 sensor. I'll show you its parameters now. Here you can see that its sensitivity is 10 millivolts per meter per second squared. It's IP type. The base frequency of this sensor is 200 Hertz. Here you can see the frequency range of the sensor and other kind of parameters. Let's apply and select this sensor. All the parameters are auto-filled and we need to enter our serial number. After that, we have some special features. For example, if you have a TED sensor, you can press Read TEDs button and the data from the sensor will automatically be read by our controller. And if you have a 3-axis accelerometer, you can enable this feature. And if you have different sensitivities on your sensor axis, you can apply this feature and enter your values. After that, we need to go to Measurement Parameters tab. And here we will enter our calibration parameters. Our first step is to set measurement mode. In back-to-back method, we are using a sine signal in case it gives us the maximum energy on the frequencies. Also, we can set the phase calculation, but in that case, we won't use it. After that, we have two important features like number of averaging and sigma limit. The number of averaging means the number of periods of collecting data from our controller. I recommend to use this number of 8 because it was tested and this value matches the best. After that, there is a sigma limit parameter. That means after we collect all our data, we calculate the average value and compare the average value with all our measured data. If some of the samples exceed this limit, you'll see a message that you need to check your setup. Also, you can select to rewrite TED's data and you can use a laser vibrometer for some setups. In that case, you need to enter transition frequency and the laser vibrometer will be set up as a reference sensor until this frequency value. If I didn't cover some of the parameters, you'll also receive a paper with detailed description of every feature. After that, you need to enter environmental parameters like temperature, pressure, humidity, power voltage, and power frequency in the lab or a room where you calibrate your sensors. You can even input it from file. Also, we have additional parameters. In some situations, your sensor may contain a capacitor which need to be charged. So you allow this feature, enter the time for charging your sensor, and after that time, the test will start automatically. Also, we have startup voltage for low frequencies. You may know that on low frequencies it takes a lot of time for your system to start up, so you can enable it into your transition frequency and the voltage value which will be sent to your shaker. In that case, you'll start up your calibration really quickly. Now we're ready to go to our equipment tab. Here you can see that our Tira TV51110 selected, and it's connected with the first output of our RLC25. Our sensor under check is connected with the first channel, and after that we need to select our reference sensor. Let's open sensor database, and I'll input a file with the reference sensor parameters. Let's find this file. It's called reference sensor, and the parameters are auto-filled. You can see its IP type, its sensitivity is 1 millivolt per meter per second squared. Let's select it, and it's connected with the second channel of our system. There are some other lines here. In case you want to cover all your frequency range, you can enter multiple shakers and multiple reference sensors. In that case, the software will show some messages where you need to place your sensor under check, and the process will be automated. And during this calibration, you'll cover all the frequency range of your sensor, and after that, all the measured data will be included into a report. Now we are ready to apply our settings. Save the test. And start measuring. On the right side, you can see that we have oscilloscope, spectrograph, some data which is being measured from our RLC25. Here in the middle, you can see the graphs, sensitivity and deviation graphs. They'll be created during the process. Here you can see the sine signal. You can even set scale settings. And after that, you can open a spectrograph. Here you can see that, here we can see our frequency. Now the frequency is changing. You'll see it in a second. Yes, now we're running at 6 Hertz. I think we have some questions now.
Yes, the question is about some spikes that they can see, that the user can see, our viewers can see on the side.
Yes, on the
like big TIHD.
I think here the user means these peaks. I think you can see that when we're running at one current frequency, we have some additional peaks. You may ask, I mean, if they are filtered or included in the measurements, but we measure only data, we get data from only one peak like shown here, and these peaks are filtered. You can see that the graph is being built now, and the sine calibration takes a lot of time, so I'll stop it for a second and tell some information about the manual mode. Sometimes you need to generate some certain frequency at level. You can enter your values here and generate. Also, all measured data is being shown here on the left side in the table. The next method of accelerometer calibration is called substitution method. During this accelerometer check, we'll need 3 accelerometers: our sensor under check, our reference sensor, and the third sensor, which is called walking accelerometer. That means this sensor has been already checked and is in use. Our first step is to place our reference sensor on the top of the walking accelerometer, and like in back-to-back method, we'll collect some data. After that, we replace our reference sensor with the sensor under check and also collect data. After that, we calculate the sensitivity using the formulas on the right side. They will be shown in the papers. This method gives you the maximum accuracy, but takes a lot of time. Let's go to settings. Here in measurement parameters, you can see use substitution method. If you want to use it, enable this feature, and you'll see some messages where you need to place your sensors. And now I won't show you this because it takes quite a long time. And we are moving to our random signal calibration.
There is a question about the distortions. Is it possible to correct the distortions?
Unfortunately, the distortion comes from the shaker and there is no way to correct it. But you can use a filter. We are using a filter which takes only the main harmonics and filters all other frequencies and harmonics. Do we have any other questions now? Can I continue? And about random signal calibration. Here you can see a graph. There is a random and sine signal data. On the x-axis, you can see a frequency range. And on the y-axis, you can see the sensitivity values which were measured on every frequency. You can see that both lines are really near to each other. And the main advantage of random signal calibration is that it takes less time than the sine calibration. It is usually used during some development of accelerometers when you need to check for about 100 or 500 sensors per day. And let's go back to this probe cell. Go to test settings. And here in the measurement parameters, you need to select FFT-H1. That means that we are going to use a random signal. Gertzel algorithm and FFT-HV are also random signal types of calibration, but I recommend to use this one. After that, we apply our settings and start. Let's continue. The system is starting up, and this type of calibration will take for about 1 minute or minute and a half. And I think it's really useful in mass production of accelerometers. Here you can see that our signals is being measured, and here you can see our random signal, and now we're running and measuring our data. Here on the left side you'll see the running progress, Here we got 7%. We will wait until the end and you will see the automatically created report. Let's open spectrograph. Here you can see our random signal spectra. Here you can see that our report is being filled automatically. There is a table with measured data on every frequency, and in the third column you can see the deviation. And it is also created in a PDF format. Here you can see the graphs and the statistics. Do we have any questions?
Yes. Is the report customizable?
Yes, I think we can provide this feature. We have some different types of templates, and we can even try to create a special template for our user. If you have any questions about reports, you can write us and we'll try to help you. Here you can see our report. I'll close it. And here you can see the statistics about the measurements, all the data. And now let's continue with our resonance search. We need to close this probe cell. And here you can see our setup. There is a steel frame with a sensor connected to its bottom, and we will drop little metal spheres through this pipe and get resonance on some frequencies of this sensor. This method is described in the ISO 60063 standard part 32. And there is the need to open this analyzer. Let's open it. And we need to select the device as a data source. Here you can see that it's loading. And now let's check our channel's configuration. Here I have only one channel selected. It's our sensor on the third channel. It is set as measuring. Its type is IPE, and its sensitivity is 100 millivolts per G. Let's start and start recording. You can see that the transient process is going, and after the recording time will start. Yes, now we can record data. I think you can see that these little steel balls are being thrown through this pipe onto the sphere. We need to make this process for about 5 or 4 times to collect the data. In the end, you'll see the signal from our sensor. And now let's stop the recording. And here we also need to stop. And after that, let's go to the data source and change back to file. We need to open our recorded file. Here you can see it's called webinar. Sorry, I need to check my key for this analyzer. Let's open the file again. Here you can see the signal. And here we got our data when the little metal ball was thrown through the pipe. Using Shift button and the right mouse button, we select this signal, press right click, and here we have an analysis feature. Let's create spectrum. And here you can see the spectrum, which was measured with our accelerometer. Let's add a cursor and move it to the highest peak. Here you can see that our resonance was captured at 12.5 kilohertz. This method helps you to find resonances on your sensors, and it is made according to the standards, so I think it's really useful in some laboratory tests for sensor producers, and I think in the next releases we will implement this feature in this probe, and I hope it was interesting for you. Do we have any questions now?
Yeah, I think there were a few questions. First one was about the report in Excel format.
Yes, our user asked us to make a feature to create a report or insert data to Excel, so it's available. If you have any questions, you can write us and I'll help you, or my colleagues will help you how to implement the data to Excel or other kind of formats.
Another one, is it possible to use an external sensor to measure temperature and humidity and implement it directly into the configuration?
I will check, but now I think there is no such feature. But I think we will develop it in the next versions.
Okay, thank you. Let me check if there are more questions. There was one about an adaptive filter, but I think you showed it.
I showed that we're filtering the peaks on the spectrograph.
Which sensors and shakers do you provide? Yeah, I can take this one. That basically we make the system, the vibration control system and the software and the amplifier. As to the shakers, we could help you find the proper configuration for your requirements for the necessary range. And yeah, it's possible that we deliver the whole system with the help of our partner shaker manufacturers and accelerometer manufacturers. Okay. Any more questions for now? Normally, best reference sensors are charge output like 8305. Do you have charge output?
Yes, we have a charge output for our controllers, and it's a built-in feature. Sorry, charge input.
Okay, any more questions? Now let me double check. I think that's it for now. So yeah, thank you very much for being here. I just want to say that we're going to send a follow-up email, and it will include an application note on our accelerometer calibration software, because you see there's quite a variety of features and like interesting little things that you can apply. So we would like you to have it in order to enjoy, like, to make the best of this software. So we'll send you the explanation on that. We also may include the recording and the presentation, if you like, into this follow-up email. And I hope that we've managed to interest you in our calibration software. It uses a variety of methods. It has quite good accuracy. Yeah, random signal calibration seems to be a nice feature for serial production tests where you need to speed up the process. The procedure is automated. As my colleague said, the reports can be customized, and they can be in different formats. Yeah, they're quite comprehensive. We also have an add-on microphone calibration module. It's kind of like a part of the same calibration module. And I think we may run a webinar on it soon, so to introduce you to this add-on feature as well. Yeah, and I hope you were interested to see the accelerometer resonance search method. It seems to be quite effective. I hope it will be interesting. I think do we have more questions? The question is, for triaxial accelerometers, does the procedure need to be repeated 3 times?
In this way, the procedure should be repeated for each axis, but there will be one report for all the data.
Yeah, so yeah, in each axis separately. Okay. And so if there are no more questions, we just wish you a very good day. So enjoy the rest of your day, and please follow us on LinkedIn and other social networks, our news updates on the website, and we'll try to inform you about our oncoming webinars and the new technologies that we have. Thank you very much for participating. Thank you for your questions. Have a nice day. Goodbye.